Hi everyone. I am Haosen Lee from Nanyang Technological University. I am presenting the work Enhancing Vision Language Compositional Understanding with Multimodal Synthetic Data. This is a joint work with Boyoung Lee. Vision language models often exhibit a bag-of-words tendency. They struggle to understand compositional relationships and attributes. For example, when presented with an image and several candidate captions that differ subtly, the model may fail to identify the correct caption. One reason for this shortcoming is the lack of subtle variation in the training data. As a result, VLMs tend to rely on coarse-grained shortcut features to maximize image caption alignment, rather than learning fine-grained semantic details. To reduce the bag-of-words behaviors of VLMs, it is crucial to train them to recognize subtle variations rather than relying solely on coarse-grained features. We propose leveraging large language models and image generation models to produce captions and images that introduce subtle variations based on real samples. By training VLMs on a combination of real and synthetic data using contrastive loss, we encourage them to better distinguish these subtle variations. We introduce Spackle, a two-stage framework that first generates synthetic captions and images, and then trains VLMs using both real and synthetic data. In the stage of generating synthetic samples, we first generate captions. For each real image caption pair, we use an LLM to edit the real caption and generate both positive and negative captions. Generating both positives and negatives prevents the model from relying on generative artifacts to distinguish between positives and negatives, encouraging it to focus on semantics in the captions instead. Then, we generate synthetic images from the real image and the synthetic captions. However, one of the key challenges lies in efficiently and accurately generating precise variations in synthetic images. To generate large-scale training images with precise variations, the image generator must satisfy three criteria. First, it must be efficient in generating a large volume of images. Second, it must ensure text alignment, meaning the generated image should accurately align with the target caption, which is subtly changed from the original caption. Third, it must maintain image fidelity, ensuring that the generated image closely resembles the real one in regions where the semantics remain unchanged. However, existing image generators struggle to meet all three criteria simultaneously. For instance, if the target caption specifies changing surfboards to shovels, the generated image should reflect this modification. While interactive image editing or per-sample optimization methods can achieve high text alignment and image fidelity, they lack efficiency. Zero-shot image editing methods often fail to make the desired semantic changes, such as replacing surfboards with shovels, resulting in poor text alignment. Text-to-image generation methods typically fail to preserve the parts of the image where the semantics remain unchanged, leading to low image fidelity. The inaccurate synthetic variations produced by these methods can mislead the learning of VLMs. To alleviate this issue, we build on a fast text-to-image model that already performs well in terms of efficiency and text alignment, and enhance it by injecting real image features into the text prompt embeddings to improve image fidelity. In text-to-image models, the prompt embeddings produced by the clip text encoder can be separated into semantic embeddings and padding embeddings. The semantic embeddings, those preceding the end-of-sequence token, primarily encode the content described in the text prompt, while the padding embeddings, those following the end-of-sequence token, typically capture the image's style. We inject real image features, extracted using the clip image encoder, into the padding embeddings to guide the model in generating images with a style that closely resembles real ones. This approach preserves alignment with the caption, thanks to the decoupling of content and style in the prompt embeddings. With the synthetic captions and images, we can combine real and synthetic samples to train VLMs with a sigmoid loss, which encourages high similarity for positive image caption pairs and low similarity for negative pairs. The challenge in training VLMs is the presence of noise in synthetic samples. The image caption similarities among synthetic samples can vary widely, introducing noise that may mislead the model during training. For example, as shown in the left figure, prompting an LLM to generate negative captions can result in hard negatives with only a single attribute changed, creating informative samples with subtle variations. In contrast, the middle figure illustrates easy negatives, where many aspects of the caption are altered, making the differences too obvious. In the right figure, when the LLM is asked to generate a positive caption, it may introduce hallucinated content that alters the original meaning, resulting in incorrect samples that can confuse the model during training. Our goal is to focus the model learning on hard samples that contain informative, subtle variations. To achieve this, we propose an adaptive margin loss. In a batch, we identify positive, hard negative, and easy negative pairs, and enforce similarity margins between them. To prioritize learning from hard informative samples, we propose adaptive margins based on the similarity differences between positive and negative pairs. When the similarity difference is less than a negative threshold, it indicates that the supposed positive pair is less similar than the negative pair, suggesting potential wrong generation. In such cases, we assign a zero loss by using a negative margin. When the similarity difference is greater than a positive threshold, the samples are already well separated, and we again apply a zero loss by capping the margin at a positive constant. For intermediate similarity differences, we design margins that emphasize learning from harder samples. Our experiments demonstrate that spackle significantly enhances compositional understanding, outperforming previous methods across 3 benchmarks. Our ablation study shows that using synthetic captions and images has a synergistic effect, and that our proposed techniques, image feature injection and adaptive margin loss, significantly enhance performance and compositional understanding. We visualize the unintended changes that image feature injection helps to reduce. In each of the 4 examples, the left image is the real image, the middle is the synthetic image without image feature injection, and the right is the synthetic image with image feature injection. The visual comparisons show that image feature injection primarily helps preserve subject size, as seen in example A, and viewing angles, as seen in example D, from the real images. For more details, please refer to our paper or code. Thank you for your attention.